Hello! We're going to go over the intro to nonlinearity slides that were presented in the kahoot a couple weeks ago. Or maybe not if you're listening to this. Might have been yesterday. First, which relationship in the Michaelis-Menten equation determines nonlinearity? Well, as we know, this is just for intrinsic clearance. We can use this Michaelis-Menten format for many other things like binding or our Emacs model or renal secretion, right? Other Michaelis-Menten type systems. So what determines nonlinearity? Well, it's this relationship here, isn't it? In most cases, the Km that we have is much greater than the concentrations that we see in the therapeutic range. And if that's the case, then the concentration falls out in importance here, and we don't have concentration as a factor anymore because our intrinsic clearance is really dependent upon Vmax, which is the capacity of the system, in the cases of enzymes, the number of enzymes available, and Km, which is the affinity for that enzyme, and that's defined as the concentration needed to achieve half Vmax, right? So it'll be all about those two factors, and concentration will fall out. If that's not the case, so if this is no longer true, if this is not true, then concentration has to stay in the equation, and therefore concentration is a determinant of your intrinsic clearance or your binding, etc. So the answer here is the relationship between Km and concentration. All right, move on. All right, which of the following should increase proportionally when dose rate increases, even if everything follows linear kinetics? So which should increase proportionally? So if we look at what are the determinants, well, first of all, if we talk about dose rate, as it increases, what else would increase with it? Well, dose rate is a determinant of CSS average, isn't it? It's bioavailable dose rate over clearance, right? So what should increase as dose rate increases? Well, CSS average, right? So we know CSS average is true. If dose rate is increasing, then CSS average would increase proportionally as long as bioavailability and clearance are remaining constant, right? So CSS average is absolutely true. If dose rate increases, would we expect for bioavailability to increase? Well, no. What's bioavailability determined by? The fraction absorbed, the fraction that escapes gut metabolism, and the fraction that escapes the first pass through the liver. Those three things multiplied together give you your bioavailability. Is this concentration dependent? No. By increasing dose rate, would you expect bioavailability to change? No, it should remain the same. So it's not bioavailability. How about clearance? What is clearance determined by? Well, it depends, doesn't it? If it's hepatic, it could be determined by Q. So is that going to have anything? Is that going to change with changing dose rate? No. It could be intrinsic clearance, enzyme activity, and binding if it's hepatically cleared, low extraction. Should those change with changing dose rates? No. So this should also be, if it's linear, if there's linearity, then you wouldn't expect to see a change in any of these. If it's cleared by the kidney, same thing, should not be concentration dependent. So clearance should be, if everything is linear, it should stay the same. It should not increase proportionally. How about half-life? Half-life is determined by volume and clearance, right? So clearance we already determined should not change with increasing dose rate. Should volume change with increasing dose rate? No, it should also stay the same. So half-life should not increase when things are linear. Now, how you determine when data indicates a nonlinearity. Here we have dose rates and resulting CSS averages. Remember, CSS average is determined by bioavailable dose rate over clearance, right? So again, as long as your bioavailability and clearance are remaining the same as we just discussed, dose rate and CSS average should be proportional, right? So as your dose rate goes up or down, the CSS average should go up or down at the same relative rate. So here our dose rate is going from 250 to 500, so it's been doubled, right? So we would expect our CSS average to also double, and it does in this case, so that's linear, isn't it? And once again, if we go from 500 to 1,000, again, doubled. Does this double? Yes. So this is proportional, and therefore linear. So does this indicate a nonlinearity? No. So this is false. How about this data? Here, instead of having dose rate and area under the curve, or dose rate and CSS average, we have dose and area under the curve. And the equation for this is area under the curve is equal to bioavailable dose, since it's a one-time thing, over clearance. Once again, these should remain constant if we have a linear situation, and therefore dose and area under the curve should be proportional, shouldn't they? So how do we test for nonlinearity? Here we go from 5 to 10. So shouldn't our area under the curve go from 150 to 300? Well, this isn't 300. This is much greater than 300. So if that's the case, our area under the curve, we have a nonlinearity here. We sure do. And it's either due to an increase in bioavailability with increasing concentration or increasing doses, or a decrease in clearance, because that's what would result in an increase in area under the curve. So does this data, I'm getting a little ahead of ourselves, but just to answer the question, does this data indicate a nonlinearity? Yes, that's true. How about this data? Now we're back to a dose rate in milligrams per day and CSS average in milligrams per liter. So we're going to, if we set up a proportion, our dose rate 1 compared to our CSS average 1 should equal our dose rate 2 over our CSS average 2, right? So if we're giving 185, forgive me for not putting the units, it's just we don't have enough space here. And we got a resulting 15 milligrams per liter, that should be equal to 195 over, and it should be 20, but let's see what we get. Let's solve for x. So 195 times 15 divided by 185 is 15.8. So instead of getting 15.8, which is what we would have gotten if it were linear, we got 20. So again, it's larger than what we predicted. So again, there is a nonlinearity. And it's either due, again, or CSS average is equal to bioavailable dose rate over clearance, over clearance. And if our CSS average is larger than what we expected, it either has to be due to an increase in bioavailability or a decrease in clearance as we increase our dose rate. So the answer here is yes, this does indicate a nonlinearity. One more of these. Okay, so I just usually pick, if I can do it in my head, I do, but this one I can't do in my, we're doing dose to area under the curve. We've got a dose of 45 with the resulting 0.5 for our area under the curve equal to a dose of 47 what would you expect for our area under the curve? So 47 times 0.5 divided by 45, I got 0.5222, and that's exactly what we got here. So this is linear, isn't it? So it's not a nonlinearity, so this is false. All right? I will see you in the next group. Thank you.